A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. Imagine a customer opening Northstar Commerce and submitting a checkout request. The browser resolves a name, establishes a protected connection, sends an application request, and expects a receipt. Along the route, an edge firewall, an application gateway, host controls, identity checks, and database access rules may each make a different decision. A green icon on one device does not prove the whole customer journey worked. This video follows that path because it keeps the subject practical. A firewall is not merely a product. It is a policy enforcement point in a system of zones, applications, identities, and evidence. Mechanically, the request enters a named zone, is compared with policy, may become part of an established connection, is forwarded only through approved paths, and produces records that operators can later inspect. The common failure is that teams say the firewall allowed it without recording which firewall, which rule, which traffic direction, which application identity, and which downstream dependency actually handled the transaction. For the Northstar Commerce simulation in this video, we will use fictional names, addresses, and log records only. Each diagram will identify the zone, the intended flow, the decision, and the evidence needed to verify it. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. NIST describes firewalls as devices or programs that control network traffic between networks or hosts with differing security postures. That definition is more useful than calling a firewall a wall. A wall suggests a single outside edge. A policy enforcement point can exist at the internet edge, between office networks, around a data store, in a host operating system, or in a cloud workload path. The question is not where a product sits in a rack. The question is which trust boundary it mediates and what access policy it can enforce. Mechanically, a firewall receives observable traffic attributes, compares them with a configured decision policy, then permits, rejects, drops, resets, routes, translates, or records the result according to its capabilities. The common failure is that a perimeter-only design assumes everything behind the edge is equally trusted, so an initial compromise can reach unrelated systems through paths that were never intentionally reviewed. For the Northstar Commerce simulation in this video, we begin every design with an inventory of zones and assets. For each arrow, identify source, destination, protocol or service, business purpose, owner, and the control that records the result. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery. Treat this as an architecture question, not a box drawing exercise. The rule, its position, and the systems around it determine the real behavior. A firewall rule has little meaning until the two sides of the rule have a purpose. Security zones group systems that share a similar exposure, data sensitivity, and operational expectation. Northstar Commerce uses an Internet zone, a DMZ for public entry services, an application zone for internal APIs, a data zone for payment records, and a separate management zone. The important idea is not the number of zones. It is that each zone has a clear default, who may initiate contact, which flows are expected, and what must never cross directly. Mechanically, zone membership supplies context before individual addresses do. The firewall can match a direction such as Internet to DMZ or application to data, then narrow the decision to an approved service and destination. The common failure is that flat networks turn every new rule into a broad exception. A rule can appear narrow by port while actually allowing an entire user subnet to reach a sensitive server class. For the Northstar Commerce simulation in this video, we make a zone-to-zone matrix before device configuration. A blank cell means no authorized flow has been identified yet, not allow while we decide later. Do not stop at whether a packet passed. Ask whether the allowed transaction is justified, observed, and still necessary after the next change. A good mental model separates traffic flow, policy flow, and evidence flow. They interact, but they do not answer the same question. At its simplest, a network policy compares packet and flow attributes. The 5-tuple is a helpful starting point: source address, source port, destination address, destination port, and protocol. Real policy often needs more context: ingress interface, egress interface, zone, connection state, time, user identity, device posture, application classification, URL category, or a threat signal. More context can improve precision, but it also makes the rule harder to test and explain. The policy should be specific enough to protect the resource and simple enough to operate. Mechanically, a packet or connection presents fields that the platform can observe. The policy engine evaluates supported fields in a defined order and selects the first applicable action or a default action. The common failure is that operators assume a friendly service name guarantees a safe rule, even though different products resolve names, track dynamic addresses, inspect encryption, and define application context differently. For the North Star Commerce simulation in this video, we record the exact match conditions in plain language beside the rule: who initiates, which service is needed, which destination owns it, how long it is needed, and where proof will appear. That is the difference between a collection of rules and a defensible boundary. The next operator can explain the decision without guessing. A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. A stateless packet filter evaluates a packet against rules without retaining a table of active sessions. It can examine characteristics such as source and destination addresses, ports, protocol, interface, and flags. This approach can be appropriate for simple, high-speed, or deliberately constrained policies. The limitation is also its defining property: a reply packet does not automatically inherit trust from an earlier outbound request. The policy must account for the direction and the expected packet characteristics, or a separate system must provide the stateful behavior. Mechanically, each packet is matched against the active rules without consulting a remembered connection record. If it matches an allow rule, it proceeds. If it matches a deny rule or reaches default deny, it does not. The common failure is that a team opens wide port ranges for return traffic because it is trying to imitate a connection table with static rules, which creates exposure that is harder to reason about than the intended client behavior. For the North Star Commerce simulation in this video, our simulated stateless policy uses only narrow, documented cases and pairs every allowed direction with an explicit verification test. We never treat a packet filter as a substitute for application authorization. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. Stateful inspection adds memory. When a permitted connection begins, the firewall stores enough context to recognize related traffic. With TCP, that commonly includes flow identifiers and connection progression. A response packet can then match an established session instead of being treated like an unsolicited inbound request. This is why a client can often make an outbound request and receive a response even though the firewall does not expose the same service to arbitrary external initiators. State is powerful, but it is not magic. It is a table with timeouts, capacity, asymmetry concerns, and implementation-specific behavior. Mechanically, the first packet is evaluated against a new session policy. If allowed, the device creates a state entry. Related packets use that entry until the session closes, times out, or the device removes it. The common failure is that people use established as a synonym for safe. A stateful firewall can confirm a relationship between packets, but it cannot by itself prove the user, application command, or business intent is authorized. For the North Star Commerce simulation in this video, we show connection state as separate evidence from the rule hit. For every test, the simulated log records whether the traffic was a new session, an established reply, or an unmatched attempt. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery. Treat this as an architecture question, not a box drawing exercise. The rule, its position, and the systems around it determine the real behavior. Most firewall policies are not sets of equal statements. They are ordered programs. The device evaluates rules according to its platform model and takes an action when a match occurs. That makes order a security property. A broad allow placed before a specific deny may capture the traffic first. A missing default behavior can turn an unknown request into an inconsistent operational problem. A default deny posture means traffic is not allowed unless a reviewed rule allows it. It does not mean users should be left without an explanation or a safe request process. Mechanically, the firewall compares traffic to rules in the configured evaluation order. The first matching rule or the highest priority decision defines the disposition, then the platform may log and count the event. The common failure is that temporary troubleshooting rules drift into permanent broad access, particularly when they lack an owner, expiry, change record, hit count, and post-change cleanup task. For the North Star Commerce simulation in this video, we name rules by intent, keep exceptions beside their approving change record, include an expiration for temporary access, and review rules that have no hits or an unexpected volume of hits. Do not stop at whether a packet passed. Ask whether the allowed transaction is justified, observed, and still necessary after the next change. A good mental model separates traffic flow, policy flow, and evidence flow. They interact, but they do not answer the same question. Network Address Translation, or NAT, rewrites addressing information so that traffic can traverse between address realms. It may hide private addressing from the public internet, publish a service through a mapped address, or support overlapping environments. NAT is often integrated with firewall products, which leads to a persistent mistake. Translation is not the same as access control. A translated address may still need an explicit allow policy. An allowed session may still be translated. The safe design documents both transformations and decisions instead of assuming one implies the other. Mechanically, the device applies a translation rule at a defined point in packet processing, creating a mapping that must align with routing, state tracking, return traffic, and the security policy model. The common failure is that a public mapping is created during a deployment and treated as harmless because the application should be protected elsewhere, leaving a reachable path that nobody owns or monitors. For the North Star Commerce simulation in this video, we keep translation rules and access rules distinct in the diagram, change review, and test plan. A verification asks which original and translated addresses appear in logs and whether unsolicited traffic is denied. That is the difference between a collection of rules and a defensible boundary. The next operator can explain the decision without guessing. A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. Ingress policy asks which sources may initiate a connection toward a resource. Egress policy asks which destinations a resource may initiate contact with. Mature designs need both. A public web endpoint may need a tightly scoped inbound path, but the workload behind it should not automatically be able to reach every destination on the internet or every system on the internal network. Egress controls help contain a compromised workload, reduce accidental data transfer, and make unexpected dependencies visible. They also require care because updates, identity services, telemetry, and business integrations may be legitimate. Mechanically, the device classifies traffic by direction relative to a protected zone and applies the relevant policy, often with stateful return traffic allowed only as a consequence of an approved initiation. The common failure is that a design hardens the front door but leaves unrestricted outbound reachability, so a compromised system can discover, contact, or transfer to destinations that were never part of its service contract. For the North Star Commerce simulation in this video, North Star maintains an egress inventory per workload. It lists update channels, DNS resolvers, identity services, payment endpoints, telemetry collectors, and any approved partner path with an owner. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. A firewall can be a dedicated network appliance, a virtual network function, a cloud security group or network policy, an operating system host firewall, or an application-aware proxy. None is universally superior because each sees a different boundary. A network firewall can govern shared paths. A host firewall can protect a machine from peers on the same network. Cloud controls can follow virtual resources and account boundaries. Application controls can evaluate requests after transport termination and identity processing. Defense in depth means giving each layer a clear job, not duplicating vague rules in four consoles. Mechanically, a request can encounter multiple enforcement points, each using the context available at that layer. The result succeeds only when the required decisions are compatible. The common failure is that identical broad rules are copied across layers, creating troubleshooting confusion and drift, while important gaps remain because no owner is responsible for the interaction between the layers. For the North Star Commerce simulation in this video, our reference architecture maps each control to the decision it owns. Shared ingress, workload interface, service-to-service access, application authorization, and data store access are documented separately. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery. Treat this as an architecture question, not a box drawing exercise. The rule, its position, and the systems around it determine the real behavior. A network firewall often makes a decision from connection metadata. An application proxy or web application firewall can operate at a different layer and may understand HTTP methods, host names, paths, headers, request sizes, known malicious patterns, rate conditions, or API schemas. That context is valuable for public web applications, but it has limits. An HTTP-aware device does not replace identity-aware authorization in the application, secure development practices, or safe network segmentation. It is another policy point with its own tuning, logs, false positives, availability behavior, and ownership. Mechanically, after a client connection is accepted and application traffic is available to the proxy, the service applies route or content-aware rules before forwarding a permitted request to the next tier. The common failure is that teams assume a WAF rule means an application vulnerability is solved, then leave the vulnerable route, authorization flaw, or unsafe backend access unchanged. For the North Star Commerce simulation in this video, we labeled the proxy as an application boundary and test it using synthetic requests. The test records which rule acted, whether it blocked or observed, and how the application behaved afterward. Do not stop at whether a packet passed. Ask whether the allowed transaction is justified, observed, and still necessary after the next change. A good mental model separates traffic flow, policy flow, and evidence flow. They interact, but they do not answer the same question. Encryption is essential for protecting traffic in transit, but it changes inspection. A network device may still see connection metadata, addresses, ports, some handshake information, volume, and timing. It cannot automatically read application content protected end-to-end. Some environments choose controlled TLS interception for certain managed devices and destinations. That is a high-impact architectural choice. It requires trust distribution, key handling, privacy review, failure testing, legal and policy alignment, exceptions for sensitive flows, and clear user communication. The goal is not to decrypt everything by default. The goal is to make a deliberate, proportionate decision. Mechanically, the policy either evaluates available metadata or routes traffic through a managed decryption and re-encryption process, then applies application-aware controls where the content is available. The common failure is that inspection is enabled without a resilient certificate, exception, and privacy model, causing broken applications, exposure of sensitive data, or blind spots that are never documented. For the North Star Commerce simulation in this video, our fictional environment treats encryption inspection as a reviewed exception. The diagram shows the certificate authority, approved population, bypass cases, logging boundary, and failsafe behavior. That is the difference between a collection of rules and a defensible boundary. The next operator can explain the decision without guessing. A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. A demilitarized zone, or DMZ, is a physical or logical segment used for systems that must accept traffic from less trusted networks. It is not a magic safe zone. Its purpose is to reduce the direct path from an untrusted source to internal resources. A public web entry service may belong in a DMZ, while business logic remains in an application zone and payment records remain in a data zone. The firewall policies between these zones should be narrow and directional. The DMZ should not become a convenient landing place for every server that is hard to classify. Mechanically, clients reach only the publicly exposed service in the DMZ. That service receives narrowly defined paths to required private services, while direct Internet to application and Internet to data paths are absent. The common failure is that a DMZ is drawn but internal management, database, or broad outbound paths remain open from it, turning the supposed buffer zone into a well-connected pivot point. For the North Star Commerce simulation in this video, we verify the DMZ by testing both the allowed public route and disallowed direct routes in a simulated policy model, then checking the deny events and the application transaction separately. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. Perimeter controls focus on north-south traffic entering or leaving an environment. Lateral movement is often east-west, one internal asset communicates with another. Segmentation adds controlled boundaries between internal zones so that a compromise in one area does not automatically become access everywhere. CISA guidance emphasizes segmentation as a way to limit movement and make traffic easier to detect and contain. The design should follow business function, data sensitivity, and recovery needs, not just IP addressing convenience. A VLAN name alone does not enforce a policy unless the paths between segments are controlled. Mechanically, internal routes pass through enforcement points or host policies that permit only documented service-to-service and management flows between designated segments. The common failure is that a network is divided into subnets but routing and access controls still permit broad any-to-any communication, creating a diagram of segmentation without the operational protection. For the North Star Commerce simulation in this video, North Star uses a small set of application dependency flows and keeps administration on a separate path. We test the normal flow, an unnecessary peer flow, and an emergency support flow with expiration. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery. Treat this as an architecture question, not a box drawing exercise. The rule, its position, and the systems around it determine the real behavior. Zero trust does not mean remove every firewall. It means do not grant implicit trust solely because a user or device happens to be inside a network. NIST frames zero trust around protecting resources and making discrete authentication and authorization decisions before access is established. Firewalls remain valuable enforcement points for segmentation, route control, egress constraints, and visibility. But a source address or network zone cannot fully answer who is acting, whether the device is healthy, whether the requested resource is appropriate, or whether access should continue after conditions change. Mechanically, the firewall enforces the network part of a broader policy while identity providers, device signals, gateways, applications, and data services contribute context and their own enforcement decisions. The common failure is that a zero-trust program only renames legacy network controls, leaving broad internal privileges and no resource-level identity or authorization improvement. For the North Star Commerce simulation in this video, we use the firewall to reduce reachable paths first, then connect each high-value flow to identity, device, application, and data controls. The diagrams label which control owns which decision. Do not stop at whether a packet passed. Ask whether the allowed transaction is justified, observed, and still necessary after the next change. A good mental model separates traffic flow, policy flow, and evidence flow. They interact, but they do not answer the same question. Microsegmentation reduces the number of systems that can communicate by default. Rather than treating an entire subnet as one trust group, policy can be tied to a workload, a service identity, a label, a device condition, or an application path. Current CISA Zero Trust guidance describes microsegmentation as limiting connections to zones or segments and notes that modern policy enforcement can extend beyond IP addresses. The value is precision and containment. The cost is policy lifecycle work, dependable inventory, labeling, dependency mapping, automated deployment, testing, and a safe way to handle exceptions. Mechanically, enforcement applies an allow list close to the workload or service path so only declared peers and methods can communicate, while unrelated peers receive a deny decision. The common failure is that a team creates hundreds of granular rules manually without service ownership or automation, then disables the controls during an outage because nobody can predict the consequences. For the Northstar Commerce simulation in this video, we begin with observed dependencies and a limited critical service, turn observations into reviewed policy, test in a simulation, and expand only when owners can maintain the evidence. That is the difference between a collection of rules and a defensible boundary. The next operator can explain the decision without guessing. A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. Firewall rules should be derived from an architecture decision, not discovered one ticket at a time. A zone-to-zone matrix captures the approved flows at a level humans can review. Each cell can name the direction, application purpose, service, or protocol, initiating zone, destination zone, resource owner, data classification, required identity control, logging expectation, and exception process. The eventual device rule is then an implementation of that statement. This separation makes change review easier because reviewers can ask whether the dependency itself is justified before debating syntax. Mechanically, a request to allow traffic is mapped to a matrix cell. If the cell does not exist, the change is a new architecture decision. If it exists, the implementation can be checked against the approved contract. The common failure is that rule collections become the only source of truth. Months later, nobody knows whether a rule supports a current service, an abandoned migration, or an undocumented emergency. For the Northstar Commerce simulation in this video, Northstar keeps policy intent in a reviewed repository. The simulated rule ID links back to its matrix entry, owner, test, change approval, and scheduled review date. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. Firewall changes can create both outages and exposures, so the workflow matters as much as the syntax. Start with a specific hypothesis. A named workload needs to initiate a named service to a named destination for a defined purpose. Document the source and destination zones, ports or application attributes, direction, expected state behavior, logging, owner, start and end time, test plan, and rollback. Apply the narrowest viable change in a controlled window, observe both the intended success and the expected denies, then remove temporary access and record the result. Mechanically, the policy is versioned, peer-reviewed, tested against a fictional traffic model, deployed through an approved path, and verified from logs and application telemetry. The common failure is that a hurried change solves a symptom but does not identify the actual dependency, so broad access becomes permanent and the original service still fails at the next hidden control. For the Northstar Commerce simulation in this video, our demo creates a synthetic allow request for the checkout API, compares it with the zone matrix, tests it against pre-change and post-change policy, and retains a rollback plan. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery. Treat this as an architecture question, not a box drawing exercise. The rule, its position, and the systems around it determine the real behavior. A firewall event can tell you that a device observed traffic and took a decision. It may record a timestamp, source and destination, ports, protocol, interface or zone, rule name, action, bytes, session identifier, threat classification, and translated address. That is valuable evidence, but it does not by itself prove a user completed a business operation. A permitted connection can still fail in TLS, DNS, identity, application validation, database access, or a downstream provider. Investigation improves when edge logs, identity events, application traces, and system telemetry share accurate time and a correlation strategy. Mechanically, the firewall emits a record at a defined processing point. Analysts join it with related records by time, session context, request identifiers, and known service ownership. The common failure is that teams declare success from an allow log and miss a failing backend, or declare a block from an absence of evidence because the relevant log category, retention, or time synchronization was not configured. For the Northstar Commerce simulation in this video, each Northstar test has an expected firewall event and an expected application event. The walkthrough asks what the firewall can prove, what it cannot prove, and which next source closes the gap. Do not stop at whether a packet passed. Ask whether the allowed transaction is justified, observed, and still necessary after the next change. A good mental model separates traffic flow, policy flow, and evidence flow. They interact, but they do not answer the same question. Denied traffic can indicate a working control, a broken dependency, a misconfigured application, a scanning attempt, or an operational change that was never reviewed. Triage should avoid two bad reflexes: automatically allowing whatever was blocked, or assuming every deny is malicious. Begin with context. Which asset originated or received the traffic? Which zone and rule acted? Is the destination expected? Is the service part of the asset's documented role? Has a release occurred? Is the pattern isolated or repeated? What do endpoint, identity, DNS, and application logs say at the same time? Mechanically, the security or operations team enriches the event with asset ownership, current deployment state, dependency inventory, and other telemetry before choosing containment, correction, or an approved policy change. The common failure is that pressure to restore service turns the firewall into a permission oracle. Any blocked flow becomes an allow rule, steadily eroding the segmentation that was meant to protect the system. For the Northstar Commerce simulation in this video, the fictional SOC playbook routes a deny to either the service owner or security owner, preserves the original evidence, and requires a documented dependency before a new allow rule can exist. That is the difference between a collection of rules and a defensible boundary. The next operator can explain the decision without guessing. A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. A firewall placed inline affects availability. It may track sessions, inspect traffic, decrypt selected flows, enforce threat prevention, generate logs, and route packets. Each capability consumes resources and can interact with traffic shape. Long-lived connections, sudden session growth, large encrypted transfers, asymmetric routing, policy compilation, log back pressure, and software updates can all change behavior. High availability is not achieved merely by having two devices. The active path, state synchronization, failover timing, routing convergence, management access, capacity headroom, and recovery tests must match the service objective. Mechanically, traffic passes through a forwarding and inspection path with finite state and processing capacity. Resilience mechanisms preserve or restore an approved path when components fail or are maintained. The common failure is that fail-open or bypass behavior is chosen casually, causing either an avoidable security exposure during failure or a complete customer outage without a tested recovery procedure. For the Northstar Commerce simulation in this video, we define the required failure behavior per service, measure capacity with safe test traffic, document a maintenance procedure, and validate that monitoring catches state exhaustion and failed policy deployment. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. A well-designed data plane policy can still be undermined if the device management plane is broad, weakly authenticated, or poorly logged. Administrators should reach firewall controls from a restricted management path using strong identity controls and least privilege. Configuration changes need approval and audit records. Backups should be protected and tested for restoration. Logs should be forwarded safely enough to survive a device incident. Emergency access should exist, but it should be time-bounded, monitored, and reviewed afterward. The firewall is not only a gate, it is also a privileged system that can reshape the network. Mechanically, separate administration traffic reaches a management interface or service through an allow-listed path, while role-based access and audit mechanisms record approved configuration activity. The common failure is that the same broad user network that is being protected can administer the firewall, so a compromised workstation becomes a path to modify the policy that should have contained it. For the Northstar Commerce simulation in this video, Northstar isolates management access, restricts administrators by role, sends configuration events to central logging, verifies backups, and rehearses recovery without exposing any production credentials. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery. Treat this as an architecture question, not a box drawing exercise. The rule, its position, and the systems around it determine the real behavior. Firewall failures are often ordinary configuration debt. The anti-patterns repeat, a broad source or destination because inventory was missing, and any service allow because a project deadline was close, a temporary exception with no expiry, a rule below a broader shadowing rule, an unused rule retained just in case, a deny policy with no useful telemetry, and a management path open from the wrong zone. These do not require advanced attackers. They create accidental reachability and make incidents slower because no one can explain why a path exists. Mechanically, policy analysis compares configured rules with evaluation order, current asset inventory, rule hit counts, change ownership, and the intended zone matrix to identify excess or dead access. The common failure is that cleanup is treated as optional after every deployment, so the rule base becomes too complex to safely change and operators eventually choose broad access to avoid breaking something unknown. For the Northstar Commerce simulation in this video, we give every allow rule an owner, purpose, source of truth, review date, and test. No hit, expired, shadowed, or overbroad rules are candidates for controlled removal. Do not stop at whether a packet passed. Ask whether the allowed transaction is justified, observed, and still necessary after the next change. A good mental model separates traffic flow, policy flow, and evidence flow. They interact, but they do not answer the same question. When checkout fails, restart less and observe more. Capture the exact user symptom, time, source context, hostname, operation, expected result, and actual result. Confirm the client reached the intended name and connection point. Check whether the relevant enforcement point saw the flow and which policy acted. If traffic was permitted, trace forward to transport, identity, application, and dependency evidence. If it was denied, compare the event to the approved dependency model before proposing any change. This sequence preserves evidence and prevents a firewall exception from masking the real cause. Mechanically, each step narrows the hypothesis by proving whether the request reached the next decision boundary. The next query is chosen from the result of the previous one, not from a guess. The common failure is that an operator tests from a privileged network or changes a rule before recording the original event, producing a misleading success that does not represent the affected user path. For the Northstar Commerce simulation in this video, the simulated incident starts with a fictional customer error, follows timestamped synthetic events through the firewall and application, applies one narrow correction, then verifies both the user outcome and the policy evidence. That is the difference between a collection of rules and a defensible boundary. The next operator can explain the decision without guessing. A firewall can allow your checkout request at the edge and still leave payment unreachable. In the next few minutes, we will trace the exact decisions that separate a secure path from a broken one. Hybrid environments do not eliminate firewall policy, they distribute it. A user may access a cloud service through an identity-aware gateway. A workload may use cloud security controls, host policy, a service mesh, and a dedicated egress point. A private link may reach an on-premises data service through another boundary. The design challenge is to keep the intent coherent. Teams should be able to answer the same questions across every location: what may initiate, what resource is protected, what identity is required, where is it logged, who owns the policy, and how is it changed safely. Mechanically, traffic crosses multiple environment-specific enforcement points while automation applies a shared policy model and observability joins records from those points. The common failure is that the physical firewall rule base is carefully governed while cloud rules, identity gateways, and host policies drift independently, leaving unexpected paths between environments. For the North Star Commerce simulation in this video, we treat each deployment location as one implementation of the same zone and service contract, then review the complete request path and return path whenever a hybrid dependency changes. Keep that chain visible: intention, enforcement, evidence, and review. CipherVibe uses the chain to turn firewall work into an operable security control. The important shift here is from a product label to a control boundary. We need to know what is being decided, from which evidence, and for whom. The final model brings the whole deep dive together. Start with resources and trust zones. Define the few flows that must exist for a business outcome. Turn that intent into explicit policies at the right enforcement points: network, host, cloud, proxy, application, and data. Maintain state awareness without confusing it with authorization. Keep ingress and egress deliberate. Use DMZs and segmentation to reduce unnecessary reachability. Treat firewall rules as controlled changes. Join logs with application and identity evidence. Protect the management plane. Then review, test, remove stale access, and rehearse incident decisions before the next outage. Mechanically, policy intent becomes enforced configuration through an approved lifecycle, while telemetry and safe tests measure whether the actual behavior still matches the architecture. The common failure is that a firewall project ends at installation, even though its security value declines when assets move, applications change, identities evolve, temporary rules persist, and evidence is not reviewed. For the North Star Commerce simulation in this video, your next action is simple: choose one high-value application, draw its actual request path, list the intended flows, compare them with policy and logs, then remove or correct one unowned exception. The practical takeaway is to make the permitted path explicit and make every exception explainable. That improves both security and recovery.